This is a short video about Gauss's lemma. This is from section 4.3 of Stein's Elementary Number Theory book. Gauss's lemma is the first thing that we need in order to prove Gauss's quadratic reciprocity law. And what is Gauss's lemma about? Gauss's lemma, it turns out to give us a way to figure out what is the Legendre symbol of A mod P. In other words, to answer the question, is A a square mod P, yes or no? And how we're going to do it is in the following way. And the book's a little bit vague about it in this paragraph here. We're going to compute this symbol in terms of the number of integers of a certain type that lie in a certain interval. Wonderful. So let's get to what Gauss's lemma says. It's going to give me another way to compute the Legendre symbol of A mod P. So pick P to be an odd prime, so anybody but 2, and just pick A to be somebody that's not divisible by P, so not congruent to P, or not congruent to 0 mod P, my bad. Here's what we're going to do. We're going to form the first P minus 1 over 2 multiples of A. I'm going to make a list out of them. Next thing I'm going to do, I'm going to take my list here, and I'm going to reduce them all mod P. But the way that I'm going to choose the representatives for each of those equivalence classes, I'm going to make sure that I choose the representatives so that they lie in this interval from minus P over 2 to P over 2. So think about that as like an interval on the real line. And again, I'm going to choose my representatives when I reduce this mod P to lie in that interval. I've got this list now again, and they're all numbers that are from minus P over 2 to P over 2. What we're going to do is we're going to go through our list and we're going to count how many of those numbers are negative. I'm going to denote that by this Greek letter nu. Then the magic is that the Legendre symbol of A mod P is just minus 1 to the nu power. There's a lot going on in that theorem. It's pretty abstract. Let's do a concrete example just to see what's going on, see if it should work out. So I'm going to pick, let's say P is 7. I'm going to pick, say, A is equal to 4. So what are the things that I care about? I need to write down what are the first P minus 1 over 2 multiples of 4. Well, P minus 1 over 2 is 7 minus 1 over 2. That's 6 over 2, so 3. So I'm going to write down the first 3 multiples of A. And I'll just write them down off the top of my head, 4, 8, 12. Now the next thing I'm going to do is I'm going to reduce them all mod P. I'm just going to do that first, and then I'll get into this interval business in a moment. So if I reduce these mod 7, so mod 7, this would be 4, 1, and 5. But now what I'm going to do is I'm going to think about, of these representatives, right, which ones of these lie in the interval from minus 7 halves to 7 halves? In other words, from minus 3.5 to 3.5. So I want to re-choose these. So re-choose, and this is me doing that. So re-choose so that we are in this interval, again, from minus 3.5, which is minus P over 2, to 3.5. All right, so like 4 is not in this interval. So what could I rewrite 4 as mod 7? 4 is the same thing as negative 3. So I'll rewrite that as negative 3. So now negative 3 lies in that interval. Cool. So again, if your representative's not in the interval, pick a different representative that is. So 4 and negative 3 are the same thing mod 7. 1 is golden. 1 is in this interval. And then 5 is also bad. 5's not in this interval, but I could rewrite that as, think of that as negative 2 mod 7. Same thing. And now that fits in the interval. So I've created my list now. I've got my list so that the first P minus 1 over 2 multiples of A lie in this interval from minus P over 2 to P over 2. Now what we're supposed to do is just look at my list. We're just going to count how many negative numbers are in that set. Well, there's 2 of them. And then here's the magic. So the Legendre symbol of 4 mod 7 should just be equal to minus 1 to the nu power, which is minus 1 to the second, which is 1. So what does that say? That says that 4 is a square mod 7, since the Legendre symbol is 1. Let's just double check that real quick. You know, is 4 a perfect square mod 7? And I see, oh, when I square 5, I get 25, which, yeah, that's congruent to 4. So yes, I square something and get 4. That means 4 is a square mod 7. So Gauss's lemma checks out. You know, surprise, it's only over 200 years old. So let's get into the actual proof of it. How do we do this? So what are we going to do again? Remember, we what? We have an A that's just not congruent to 0 mod 7. I make this list of the first P minus 1 over 2 multiples of A. I'm going to reduce them mod 7. And so each of these things, I'm going to reduce them mod 7, and again, I'm going to pick the representative so that it lies in this interval from minus p over 2 to p over 2. Like, you can always do that. I just showed you can always do that. I just showed you can always do it by one example. That's bad logic, but I'm just showing you it's not necessarily hard to do. Now, if I'm going to be in that interval from minus p over 2 to p over 2, then all your representatives, they have to be things that look like this. Now, this is a little bit tricky. I'm not saying that I'm not saying these two sets are equal. I'm just saying when you reduce mod 7, that each of these should turn into one of these. So potentially this set that I've highlighted is bigger than S up here. But the point now is that everybody's represented this way. Now, what do we need to be careful about here? Well, how do I know that when I reduce all these things mod 7 and choose the representative so that it's between p minus p over 2 and p over 2, how do I know I don't get like two of the same thing? How do I know that? So how do I know that no number appears more than once when I reduce it mod 7? With either choice assigned in that case. And so let's talk about, well, what if it did? Well, that would mean that, say, two elements of this set here are congruent modulo p, but that can't happen because of the cancellation property that we have modulo p. So for instance, right, if like Ka was congruent to, I'll pick a different letter like Ja mod p, in that case, that would just say that K is congruent to J. But that's impossible because K and J are both things that are less than p minus 1 over 2. That's less than p, right? So these things can't be congruent mod p. So that is false. And in fact, what also can't I have? I also can't have, I guess, what else could happen? So if it did, then either two elements are congruent mod p. I just tried to justify that that's not true, since k and j are both less than or equal to p minus 1 over 2, which is less than p. And the other possibility of what else would that imply, or that could mean that the sum of two elements from S is 0. So how could that be? What if the sum of two elements from S, again, two of these, Ka plus Ja again, what if that was 0? So let me get rid of this so that it's just kind of out of the way. What if Ka plus Ja was 0 mod p? But remember, K and J again are smaller than p minus 1 over 2. So I know in particular, right, that K and J can't be congruent to each other mod p. Right? There are p distinct equivalence classes, and they represent two different equivalence classes. But again, by cancellation, right, we could factor out that A and cancel since p is an ice prime, and we get a lot of those cool cancellation laws whenever the modulus is prime. So what that leads to, again, is that K plus J has to be 0 mod p, which of course is silly since these things are less than p minus 1 over 2. So what should we have then? We should have the resulting set that we get, of the representatives that we choose when I reduce these mod p and I choose the representative so that they occur somewhere in here. I could always rewrite them as just either like legitimately like 1 times that element, p minus 1 over 2 or 2 or whatever, or negative 1. So each of these little epsilons is just a placeholder for either 1 or negative 1. So I'm just picking the ones that I need out of that interval there. So what can we do with that now? What we're going to do is let's multiply all the elements of S together. Well, that's right here when I multiply those all out. And what else could I do? I'm going to also multiply all the elements of T together. Now, what we just talked through is like, how do you get T? That's just me reducing things mod 7 and picking the elements or the representatives so they're between p minus p over 2 and p over 2. So they should be equivalent mod p. And so when I multiply everything in the green together, I hope it makes sense that those two products need to be equivalent to each other, right? We're multiplying the same things together, mod p. But if we think through what's going on over here, I'm going to rewrite this. This is A, and how many times do I multiply A by itself? Well, look, this number is counting how many times. So this is really going to be A to the p minus 1 over 2 power, times this product, 1 times 2 times 3, up to p minus 1 over 2. All right, so why is that cool? Well, because then I see that, what else can I do? I've got all these 1, 2, 3 up to p minus 1 over 2 being multiplied on the left. I've also got those being multiplied on the right. And again, since this modulus is prime, we have cancellation. I can cancel, I can divide, the 2's divide, the 3's divide, etc. The p minus 1's over 2's divide. So what do you get? What are you left with? All you're left with when the dust settles, let's get a different color, you're left with my power, a to the p minus 1 over 2, and that's equal to the product of all these little epsilons. And remember, these epsilons are placeholders for whether you needed a positive or a negative. So all the dust settled, and I've got that, a to the p minus 1 over 2 is congruent to the product of all these 1's and minus 1's modulo p. Now, why is this good? Why is this important? This a to the p minus 1 over 2, that power should look familiar, and it's from proposition 4.2.1. What did it say? This is Euler's criterion, which is the previous video, and what it guaranteed me that the Legendre symbol of a mod p is always going to be equal to a to the p minus 1 over 2. It's always going to be that power there. So if I think about that this power then represents the Legendre symbol, what are we saying then? We are saying that what is this then? This should just be, it should just be dependent on, right? How many negative numbers, how many of these epsilons are negative? And what did we say was going to represent how many of these epsilon is negative? That number that represents how many of these are negative is what we're calling nu. So this could be rewritten. This product of epsilons is minus 1 to the nu power. So to finish Gauss's lemma, what we needed to invoke, again, was Euler's criterion, which gave us this way to think about the Legendre symbol.